Hello everyone, welcome to this lecture series in linear algebra. This is lecture 14 and today we are going to talk about inner product, length of a vector and orthogonality. First let us talk about the inner product, which is also known by the name dot product or scalar product. So if you have two vectors u and v in Rn space, then the product calculated as u transpose v is called the inner product of u and v and is often written as u dot v or inside this bracket as u dot v. Okay, so that means inner product of any two vectors where both vectors belongs to same space is calculated as the transpose of first vector times the second vector. Okay, so if u and v are in Rn, that means there are n elements, so they are column vectors. So u transpose will take care to make it a row vector of same size as the number of elements in the column of v, so the product is possible. Okay, so this row vector when multiplied to this column vector, it will give a scalar quantity. Okay, so if you are given u vector in Rn, so it will have n elements. V vector is also in Rn, so it will also have n elements. And so the inner product of u and v is u dot v, or which is u transpose times v, and because the column vector, so it becomes a row vector when we take transpose. So this product of u with v is possible with this row multiplied with column, so u1 v1 plus u2 v2 plus so on un vn. So it's a scalar quantity. Okay, now the inner product has certain properties, and so for that we have vectors u v w in the Rn space, and let's C be any scalar. Then the first property is that the inner product is always commutative. That means if you calculate u dot v or you calculate v dot u, it gives the same scalar value. Okay, so commutative property holds in inner products. Second, the associativity, that you add two vectors and then take the inner product with third vector, or you take the inner product of first vector with third and second vector with third and then add those scalars. They give the same value. Okay, so associativity also holds. Third is that you scale a vector and then take inner product. Okay, or you scale the second vector and then take the inner product with first, or you take the inner product first and then you multiply with the same scalars. Okay, so either way it gives the same value. Okay, the fourth property is that the inner product of a vector with itself is always greater than equal to 0, and in fact it is equal to 0 only in the case when the vector itself is a 0 vector. Okay, so inner product for non-zero vector with itself is always strictly greater than 0. Okay, these two conditions, second and third, they, when we combine these two, these can give us a very useful generalized result, that the linear combination of vectors, if you take its scalar product or inner product with a vector w, this can be same as calculating the inner products and then their linear combination. Okay, so the inner product of linear combination with a vector is same as the linear combination of inner products. Okay, so this is very useful result. The second definition is the length of a vector, which is also called the norm. Okay, so the length or norm of a vector v is a non-negative scalar denoted as norm v. So inside the double lines, the v vector is written, means it's the length of vector or norm of vector, defined as the square root of the vector dot product with itself. Okay, and if v is a non-zero vector, then definitely this quantity dot product is positive, strictly positive by the property. So this root is will give us the length of that vector. Okay, and if this belongs to Rn space, then it will have n elements, say v1 v2 v3 so on vn. Then this dot product is easily you can see is v1 square plus v2 square plus so on vn square. Okay, So elements of vector v, each element squared, sum and its under root, that will be the length of vector. Okay, and norm square will be simply dot product of vector with itself. Okay, so if you have a vector in R2 space, okay, that means a vector has only two elements. A v vector can be written as a b. Okay, then the length of this vector is, length square is v dot v. Okay, and so inner product of this vector with itself, and we know it is equal to v transpose v. So this column becomes row times the same column. So it is equal to a square plus b square. So that means if I to calculate the length of vector, it is square root of a square plus b square. Okay, and if you remember R2, if is a plane, so if we note down this v vector, the position of this on the plane, so geometrically this length, which is calculated at a square plus b square under root, coincides with the standard notation of length of the line segment from origin to v. Okay, so geometrically if you draw the R2 the plane and you note down the v vector as a comma b, then the length of vector by this law. Okay, the hypotenuse square is base square plus perpendicular square. Okay, so immediately you see that this length of the vector which we can calculate from here geometrically is same as by this definition. Okay, and so this holds for not just for R2 space but for R3, R4, so on in general Rn space we can use this definition to find the length of a vector. Now one small result here, that for any scalar c, the length of the scaled vector is modulus of c times the length of the vector. Okay, or this norm of v. Okay, that is uh, the length of cv is same as modulus of c times length of v. Okay, so proof of this is very simple, that if you calculate the left hand side squared, then length of cv squared is, we know norm square is the vector multiplied with itself, so cv multiplied with itself, the dot product, and by property the constant goes outside, so it becomes c square v dot v, and v dot v is the length of v squared. Okay, so if we take square root on both sides, okay, then immediately we have that the norm or length of this vector cv is modulus of c times length of v. Okay, because length is a non-negative quantity, so we have to take modulus here. Okay, uh, another definition is the unit vector. Okay, so a vector whose length is 1 is called a unit vector. Okay, so given any vector, we can always find the unit vector by dividing the uh, that vector with its length. Okay, so if we divide a non-zero vector v by its length, then the vector u, which is v by length of v, is a unit vector. Okay, so if you are given any vector, you can divide that vector with its length to produce a unit vector. Okay, so this process of creating a unit vector from any non-zero vector is called the normalizing of the vector. Okay, normalizing process. The vector u is in the same direction of v. Okay, so this u and v are in the same direction. Okay, so direction do not change, only we are scaling the vector v down to a unit vector. Okay, or up to a unit vector, depending upon whether v length of v is less than 1 or bigger than 1. So for example, say let v be a vector, okay, in R4, and find a unit vector u in the same direction as v. Okay, so what we have to do is first find the length of v and divide the v with length of v to find this unit vector. Okay, so the length of v we know is given by root of v dot v, and it is element squared and added and its square root. Okay, so each element squared and added, okay, and its root. Okay, so clearly you see that length of v vector is 3, and if I divide the v vector with this length, then we will get unit vector. Okay, so unit vector u is v by its length, so 1 by 3 of this vector. Okay, so this is a unit vector. So if you square and add the elements and take a square root, then you will find that the length of u is 1. Okay, the Another definition is the distances in Rn. Okay, so for any two vectors u and v in Rn space, the distance between u and v is written as distance uv is the length of the vector u minus v. Okay, so we can calculate the distance between the two vectors by calculating the length of the u minus v vector. That means distance between u and v vector is length of u minus v. So length of u minus v is written as norm of u minus v, and it is by definition square root of the square of elements in this u minus v. Okay, so if u has elements u1 u2 un, v has elements v1 v2 vn, then u minus v will have elements u1 minus v1 u2 minus v2 so on un minus vn. So sum of square of those elements and its under root, that will give us the distance between u and v. For example, say if we have to compute the distance between the vector u, which is in R2 7, 1 and v again in R2 3, 2, then we first need to calculate u minus v vector, and then from there we can calculate the length of the vector. Okay, so if you calculate u minus v, then 7 1 minus 3 2. Okay, so immediately you find that u minus v is this vector 4 minus 1. So length of this vector you can calculate as sum of each element squared. Okay, so 16 plus 1 and its root. Okay, so immediately you have that root 17 is the distance between u and v. Another definition here is the angle between vectors in Rn. So if you have two vectors u and v are non-zero vectors in Rn, then the cosine of the angle theta between the vectors is given by cosine theta equals u dot v over length u into length v. Okay, so that means the angle between two non-zero vectors can be easily calculated by calculating the cosine of the angle, which is equal to the inner product of the vectors divided by length of each vector. Okay, and interestingly, if these two vectors are perpendicular, that means this angle is 90 degree, then cos 90 is 0, and so the right hand side tells us that u dot v is equal to 0. Okay, so if vectors are perpendicular, then inner product must be 0. Okay, so this will be our next definition of orthogonality. Okay, so orthogonal vectors means perpendicular vectors. So two vectors u and v in Rn are orthogonal to each other if u dot v is 0. Okay, so that's true, because if cos of 90 is 0, then this has to be 0 to satisfy the definition. So small note here that the 0 vector is orthogonal to every vector in Rn, because it satisfies that 0 dot v vector is 0 for any v vector in Rn space. Okay, so you take any vector in Rn space, its dot product with 0 vector is always 0. So this equation is satisfied for every v and 0 vector. That means 0 vector is perpendicular to every vector in Rn space. Okay. Small theorem, the Pythagorean theorem, which says that two vectors u and v are orthogonal if and only if the length square of u plus v is same as length square of u plus length square of v. Okay. The proof of this is simple, that if we start with the left hand side, then u plus v norm square is same as dot product of this vector with itself. So u plus v dot with u plus v. By property we can rewrite it as u dot u plus u dot v plus v dot u plus v dot v. Okay, and then u dot u is norm square, v dot v is again norm square, and u dot v is 0 if u and v are orthogonal, and because u dot v is always equal to v dot u in inner product, so v dot u is also 0. So if u and v are orthogonal, u dot v and v dot u are 0, so immediately this equals this. Okay, so that's a very simple proof. Now one important definition here is the orthogonal complement. Okay, so if a vector z is orthogonal to every vector in the subspace w of Rn. Okay, so if you are given a vector space Rn and w is a subspace of it, and then if you know that if there is a vector z which is orthogonal to every vector in this space. That means if you take any vector from here, its dot product with z is 0. Okay, then z is said to be orthogonal to this whole subspace w. Okay, so z is orthogonal to subspace w. That means you take any vector from w, say x is a vector in w, then z dot x is 0. Okay, uh, the set of all such vectors z, okay, that are orthogonal to subspace w of Rn is called the orthogonal complement of w and is denoted by w perpendicular. Okay, so all the vectors which are orthogonal to this subspace, they will form a set, and that set is called the orthogonal complement of w, and it is denoted by w perpendicular. Okay, so w perpendicular is the orthogonal complement of w. That means if you take any vector in w and any vector in w perpendicular, their dot product is 0. Okay, so if x belongs to w and y belongs to w perpendicular, then x dot y is 0. For example, say in R3 space, there is a subspace W of R3, which is a plane passing through origin, and say there is a line L passing through origin which is perpendicular to this plane. Okay, so that means if you take any vector along the line and any vector in this plane w, then the dot product of those two vectors is 0. Okay, so if you take this z vector in on the line and w vector on the plane, then dot product of w and z are 0. Okay, and this is true for any arbitrary vectors that you take from w space and l space or l line. So that means this w space is orthogonal complement to l line. Okay, also that we can write that w perpendicular is equal to l. Okay, because w perpendicular is the orthogonal complement of w in the perpendicular direction. So w perpendicular, we can write it equal to line l, or line perpendicular is equal to this w. Okay, they are orthogonal complement to each other. One result from here is that if w is a subspace of Rn and w perpendicular is the set of all vectors orthogonal to w, then w perpendicular is also a subspace of the same space Rn. Okay, so if w is a subspace of Rn and there is a orthogonal complement set to this, then that set is also subspace of Rn. The proof is simple, that we have to prove the three properties. The first property is that zero vector should be in this space. So clearly it is true, because zero vector is always orthogonal to every vector. Okay, so zero vector is definitely in this space. Okay, so that means if you take zero vector from here and any vector from w space, their dot product is 0. Okay, which is always true. Second property is that we have to take two vectors in w perpendicular and we'll prove that their sum is also in w perpendicular. So let z1 and z2 are in w perpendicular, and if they are in w perpendicular, their dot product with any vector in w will be 0. So let u represent any vector in w. So immediately we have that z1 dot product with u is 0 and z2 dot product with u is also 0. Now if we calculate this z1 plus z2 dot product with u, then easily you can see that it is z1 dot u plus z2 dot u, and because these two are 0, so this sum is also 0. So immediately we can see that z1 plus z2 is a vector which is orthogonal to u. So z1 plus z2 belongs to w perpendicular set. Okay, because u belongs to w set. So clearly for any two vectors z1 z2 in w perpendicular, the sum z1 plus z2 is also in w perpendicular. Now we have to prove that for any vector z1 in w perpendicular, the scalings constant times z1 is also in w perpendicular. So again, let z be any vector in w perpendicular and u represent any vector in w. So clearly z dot u will be 0. Okay, because these are orthogonal complement. Okay, and so if I calculate now c times z dot product with u, okay, for any scalar c, cz scaled vector dot product with u, then this can be written as c times z dot u by the property, and z dot u is 0, so constant times u is 0. Okay, so clearly cz vector dot product u 0 means cz vector is orthogonal to u vector. Okay, so this means that cz vector belong to w perpendicular. So all the three properties are satisfied, so W perpendicular must be a subspace of Rn. Okay, so this is the result. Now one theorem, okay, say let A be a M cross N matrix. The orthogonal complement of row space of A is the null space of A, and the orthogonal complement of column space of A is the null space of A perpendicular. So again, this theorem says that if you are given a matrix M cross N, that means there is a transformation from Rn to Rm space, then if you know the row space A, then its orthogonal complement row space A whole perpendicular is the same set as the null space A. Okay, so that's what is the first result, that the row space A perpendicular vectors, okay, the vectors which are perpendicular to row space A are in null space A, and the vectors in null space A actually are in perpendicular set to row space A. And secondly, the orthogonal complement of column space A. Okay, so the column space A perpendicular set is same as null space A transpose. Okay, null space of A transpose. Here it is A transpose, not perpendicular. Okay, A transpose. So it is A transpose here. So we are going to prove these two results. First is that the orthogonal complement of row space A is null space A, and secondly the orthogonal complement of column space A is null space of A transpose. Okay. So first this result. So we are going to prove that you take any vector here in row A perpendicular, it belongs to null space A, or you take any vector in null space A, it belongs to this set. So these two sets are just same. Okay. So let us prove this. Say let X belongs to null space A, we will prove that it also belongs to this set. Okay. So if any vector belongs to null space A, that means this vector will satisfy the homogeneous equation Ax is equal to 0. Okay. So then Ax is equal to 0, and so X vector is orthogonal to each row of A. This is because A matrix, when multiplied with the column vector X, then the multiplication is that the each row of A is multiplied with X vector, and it gives the right hand side vector which is 0. Okay, so first row when multiplied with X vector gives 0 element, second row when multiplied with X vector gives the second 0 element, and so on. That's how the homogeneous system is written. So that means X vector is orthogonal to each row of A. Okay, but the row space of A is a linear combination of rows. Okay, so since row space of A is span of rows space, okay, so X is orthogonal to row space A. Okay, and if X is orthogonal to row space A, that means X belongs to row space A perpendicular set. Okay, so that's our one side. Conversely, if X belongs to or orthogonal of to row space A, okay, that means X belongs to row space A perpendicular, then it means that the dot product of any row of A with X is 0. Okay, so that means X is orthogonal to each row of A, and that means that A times X is 0, because this is how we write that each row of A times X is 0. Okay, so this is how each row of X A with X is orthogonality. Okay, so this implies that this homogeneous system is satisfied, then X belongs to null space of A. This implies that X belongs to null space A. So every vector in null space A belongs to row space A perpendicular, and every vector in row space A perpendicular belongs to null space A. That means these two sets must be equal. Okay, so this proves our first result, that row space A perpendicular is null space A. Now this first statement is true for any matrix A. Okay, so it must be true for the A transpose matrix. Okay, so since it is true for any matrix, it is true for A transpose matrix. So I can put A transpose here, it will be satisfied. So row A transpose perpendicular must be equal to null space A transpose. Now row space A means linear combination of rows, and A transpose means that the columns are changed with rows. Okay, and rows becomes columns. So row space of A transpose means the linear combination of columns, because columns are transformed into rows, and then it's a linear combination of those rows. So it is the column space of A which is the row space of A transpose. Okay, so uh, it is true then that the row transpose of A row space of A transpose is same as the column space of A. okay, because column space is linear combination of columns of A, and row space of A transpose means the columns of A are written in row, and row space is the linear combination of rows. So these two must be same. Okay, so we can substitute it here, and we have that the column space A perpendicular is null space of A transpose, which is our second result. Okay, so this was about orthogonality. In this lecture we'll do up to here, and in the next lecture we'll continue with this topic, and we'll define what are orthogonal sets, what is orthogonal projection, and how we can utilize this process, the very famous Gram-Schmidt process. Okay, till then, have a very nice day.